Hey everybody, happy Thursday. Yeah, almost there to your second break. Um, just a heads up for you guys. Tomorrow, I'm not going to be in the building. I have a funeral. So if you guys have something that you need or anything like that, just send it to my email. And I just apologize if I don't get to it until later or something like that. I know it's the last day of the quarter, but for the most part, I mean, we don't really have anything else to do, so it shouldn't be too bad as far as needing me, as far as like questions or anything like that. So just a heads up for you guys. All right. Yesterday we talked about compound interest. Today we're going to talk about a couple problems. What do we do if we want to model a problem exponentially, but maybe it's not banking that we're looking at, okay? So it depends on what's going on with exponentials, because we can either have exponential growth problems or exponential decay problems. All right, let's say we had something like the population of Brazil was 32,400,000 in 1980. Each year, it grew by 3.1%. How many people live there? In 2020. I guess 2021. We'll make it easy on ourselves. We'll just say 2020. Okay. So pretty much if we see a percentage change, you know that you're going to need to use an exponential function to model that. All right, so this year, or I'm saying each year that this thing grew by 3.1%, that means we're going to need to use an exponential model. And the model is going to look very similar to what we did yesterday. We're going to do f of x. I'm not sure where to write this. We'll write it underneath here. F of x equals a, or p, that could be p there, times 1 plus r to the t. So if you can look, you see that there's definitely some similarities between what we have done so far, right? You see the a there, that's like our principal, our initial value. It's in the y-intercept spot, so that's kind of how we know it's like one of our initial values, right? We also see that we have inside the parentheses 1 plus r. That's our rate, just like it was yesterday. And we still, every single time that you have a percent in a problem, you have to change it to a decimal. That is like rule number one with percentages, okay? And then the t is still going to represent time for us. So pretty much very similar to what we saw yesterday. But this can be used to model anything with a percentage that's changing. So, the population is obviously a very popular one that is modeled exponentially. But you could also see, like growth of bacteria. That's another really big one. Or spread of a contagion, like COVID. That's exponential as well. So when we set up ours here, let's see here. I know the initial amount was 32,400,000. So 32,400,000 times, I don't know why I didn't just write this underneath, actually. We'll make it curve. It'll be fun. And then usually what I do is I just kind of add this right away. So 1.031 to the, and then from 1980 to 2020, that's what, 40 years? 90, 2000, yeah, to the 40th power. So when you're setting it up, it looks ridiculous like that, by the way. That's pretty fun. When you're setting it up, our initial value, 1 plus the rate, because it's growing, and then our t is out here, right? It's pretty self-explanatory. So we got 1.031 to the 40th times 32,400,000. And I got a population of, what'd I get? 1, 0, 9. And it's 0.6, I guess we'll round up to 2, because you can't have, like, you know, part of a person here. So it looks like in 2020, there would have been 109,873,162 people who lived in Brazil. Okay? So this guy here, this is the important part. Initial value, 1 plus the rate, and then to the time. Now what about what's going on when we have decay? Because they're going to be really, really similar. So let's say you have a man. Can you guys see green on there? Oh yeah, you can see that. A man takes 100 milligrams of Motrin. That breaks down at a rate of 38% each hour. How many milligrams are left in 4 hours? Okay, this is another really good exponential model, and it's medicine breaking down in your body. Medicine has time release so that it helps you now and it continues to help you. And that's kind of how it breaks down in your body. It's exponentially. So it breaks down some, then some more, then some more, then some more, then some more. So the difference here is that we see that we're decreasing, right? This thing is breaking down. So when we come up with our formula, you know, our f of x here, I guess, yeah, maybe sometimes you'd see it, I should probably write it this way. Amount, just like you did here, and this could be principal still. Like those are usually just words that we use in banking, but it's still the same idea. So I'm just going to write it f of x equals, and then a times the quantity, 1 minus r to the t. Now what's interesting here is you can see that on the inside now, you can see where our decay is going to come from, because what we're going to do is we're going to subtract the rate, right? So it's actually going to be less than 1 because it's breaking down. If you want to think of it in another way, What's left on the inside is how much we have left every hour, right? We have this much, what percentage of it we have left. So if we set this one up, the amount that we started with is 100. Let's see if we have space this time. 100 times quantity 1 minus 0.38, all to the 4th. Cool. So on the inside here, our common ratio, if you will, we're going to have 1 minus 0.38 would be what? 0.62 to the 4th. So you can see this number is less than 1. That's where the decay comes from, right? That's why we're decreasing. So we're just going to keep 62% of it each time. So in this case, we are going to do 0.62 to the 4th and times that by 100. And after 4 hours, you would still have 14.776 milligrams of Motrin in your body. So this is why you're not allowed to take medicine just as often as you want, right? They tell you you have to wait 6 hours. This is why. Because it's still in your body, and if you take too much of it, obviously that is not good for you. So you have to wait till it is such a low amount left in your body that it's, doesn't matter basically, and then you can have more medicine for your headache or whatever you have. All right, you guys. Yeah, that's it from me. Pretty nice. Let me know if you have any questions today. And like I said, I probably won't really talk to you tomorrow. So have a great second Christmas break here. Enjoy your week off. And some of you, I'll see you in class on the Monday that follows. All right? See you later.